Hello and welcome. Let's go back to 1872. It was in this year that the German mathematician Karl Weierstrass introduced a counterexample that shocked the mathematical community. He presented a function that fundamentally altered the way mathematicians understood real analysis. Here is the definition. At first glance, it looks like a standard trigonometric series. We define f of x as an infinite sum starting from n equals 0 and going to infinity. Inside the sum, we have an amplitude factor, a to the power of n, multiplied by a cosine wave with an exponentially increasing frequency, b to the power of n times pi x. But to truly understand why this specific formula was so unsettling for the mathematicians of that time, we first need to clarify two core concepts: continuity and differentiability. First, let's look at continuity. Intuitively, a function is continuous if there are no breaks, no jumps, and no holes. To understand this rigorously, let's look at the geometric interpretation on the right. Here, the red curve is the graph of our function f of x. The blue dot marks the point at x equals c. Notice the brown horizontal band. This represents epsilon. It defines a tolerance range from f of c minus epsilon to f of c plus epsilon. We require the function's values to stay within this strip. Now, look at the green vertical band. This represents delta. It captures all x values that are sufficiently close to c, specifically between c minus delta and c plus delta. The core meaning of this picture is simple. If we pick an x inside the green delta zone, the corresponding point on the graph must land inside the brown epsilon zone. If, for every epsilon band, no matter how thin, we can find a corresponding delta window, then the function is continuous. This leads us to the formal definition. We say that a function f is continuous at a point c if three conditions are met. First, the function must be defined at c. Second, the limit as x approaches c must exist. And finally, the limit must equal the actual value of the function. To make this absolutely bulletproof, we use the epsilon delta definition. It states that for every epsilon greater than 0, there exists a delta greater than 0, such that if the distance between x and c is less than delta, then the distance between f of x and f of c must be less than epsilon. In visual terms, this means for any target range around the function's value, we can find a small enough window around x to satisfy it. To understand the unique nature of the Weierstrass function, we must first revisit the geometric meaning of differentiability. Consider this blue curve, representing a standard smooth function, f of x. We fix a point A at position C and introduce a second point, B, at a distance h away. The line connecting them, the yellow secant line, represents the average rate of change. Its slope is the difference quotient, delta y over h. Now, let's apply the definition of the derivative. Watch what happens as we take the limit as h approaches 0. As h gets smaller, point B slides along the curve, getting closer and closer to point A. Notice the secant line. As the distance vanishes, it rotates and eventually settles into a unique limiting position. This final yellow line is the tangent line. If this unique tangent line exists, the function is differentiable at point C. Visually, this implies local smoothness. However, as we will see shortly, continuity does not always guarantee this smoothness. Now, let's examine the famous counterexample, the Weierstrass function. This function is defined as an infinite sum of cosine waves, where the frequency increases and the amplitude decreases with each term. Let's build it step by step to see why it breaks calculus. At n equals 0, we start with a standard cosine curve. It is smooth and has a tangent line everywhere. When we add the next term, notice the ripple. The frequency triples, but the height is cut in half. As we continue adding terms, n equals 2 and 3, we are essentially adding wrinkles on top of wrinkles. Now, let's take the limit to infinity. Look at the resulting graph. It is continuous, meaning there are no breaks or holes. You could theoretically draw it without lifting your pen. However, it is differentiable nowhere. Why? Recall that for a derivative to exist, the curve must look like a straight line when you zoom in. But here, because of the self-similar fractal nature, the jaggedness never goes away. No matter how close you look, the graph remains sharp and oscillates infinitely. Since it never smooths out, no unique tangent line exists at any point. And now, we proceed to the final task, the integration of the Weierstrass function. First, let's define the problem. We consider the function f of x given by the infinite series, the sum from n equals 0 to infinity of a to the power of n times the cosine of b to the power of n pi x. We must make two important assumptions. First, we assume a is strictly between 0 and 1. This is a necessary condition for uniform convergence. Second, while b is often an odd integer in the classical definition, for the purpose of integration, we treat it as a real number. To evaluate the integral, we seek to interchange the order of summation and integration. This operation is valid only if the series converges uniformly. To prove this, we apply the Weierstrass M test. Since the absolute value of the cosine function is less than or equal to 1, it follows that the absolute value of our general term is less than or equal to a to the power of n. Given that a is less than 1, the geometric series of a to the power of n converges. Therefore, the original functional series converges uniformly on the entire real line. This implies that f of x is continuous and consequently integrable. Now, let's solve this step by step. We consider the integral I over the interval x1 to x2. By virtue of the uniform convergence we just established, we interchange the order of operations. We pull the summation and the factor a to the power of n outside the integral. We now compute the integral of the general cosine term. The antiderivative of cosine b to the n pi x is sine b to the n pi x divided by the inner coefficient b to the power of n times pi. Applying the limits from x1 to x2, we get the difference of signs divided by b to the n pi. Substituting this result back into the summation, we can simplify the expression. We factor the constant 1 over pi out of the sum. Notice that we can group the terms a and b, giving us the ratio a over b raised to the power of n. In conclusion, the Lebesgue integral of the Weierstrass function over an arbitrary interval is given by the following formula: 1 over pi times the infinite sum of a over b to the power of n multiplied by the difference of the sign terms. A special case to note: if we integrate over the period 0 to 2 and b is an integer, the sign terms vanish. In this instance, the total integral equals 0. This makes sense, as we are integrating an oscillatory function over a complete set of periods.